Okay, we're continuing on. I'm going to get to number 20. I want to see if I could finish these problems within this video. 20 has x equal a sine, a cosine, and y equal 3 the sine. Well, anytime I see trig, I'm going to think of identities. And to be specific, mainly it turns out to be in this class and your second semester calculus, we're talking about the Pythagorean identity. The reason for that, I see sine and cosine, tan and secant, cotan and cosecant. I do know that sine squared plus cosine squared equal a 1. So if I isolate the cosine by itself and I square both sides, I'm looking at cosine squared of t equaling x squared over 2. If I isolate the sine by itself, sine of t would equal y divided by 3, and if I square both sides, I'll get y squared over 9 equals sine squared of t. And I know if I add the right side, sine squared plus cosine squared is a 1, and that would be an x squared over 4 and a y squared over 9. I messed up on this part. When you square both sides, you end up with a 4. So I know that this is a circle, and I know this circle is actually, I'm going to stretch 2 units in the x, 3 units in the y. I'm sorry, did I say a circle? Oh, you guys forgive me. I meant an ellipse. Just seeing if we're paying attention. That's what the ellipse looked like somewhat, but I'm tracing a portion of that ellipse. At t equals 0, where am I? Throw 0 in there. Cosine of 0 is 1, that's a 2. Sine of 0 is 0, 1, 2, I'm right there. At t equal pi over 2, not wise to pick integers. Cosine of pi over 2 is 0 times 2, that's 0. Sine, that's a 3. 0, 3 is right there. So I know I traced this upper portion of the circle, of the ellipse, and if I go to pi, I'll notice that at pi, cosine is negative 1, that's a negative 2, and sine is 0. And I just want to make sure that you don't mix things up. I don't want you to say, look, 0 to pi, I know that 0 to pi really looks like, come on. I don't want you to think that I could just run from 0 to pi and that's the direction. That's not true. And that's why I made an example. It's going to come up on your homework problems, but I wanted to make sure that I touch on it here before you get to the homework. So the next problem on the list would be as follows. If I look at this problem, say, okay, well, I'm going to make use of that trick again. X minus 1 equal twice the sine of t, and x minus 1 over 2 equals sine of t. And if I square both sides, I'll be looking at x minus 1 squared over 4 equals sine squared of t. Of course, there's other ways of doing these problems. I'm choosing this way. And if I isolate this cosine by itself, divide by 4 both sides, and if I square both sides, I will get y squared over 16 equals cosine squared of t. And if I add the right, I'll get a 1. And if I add the left, and this would be another ellipse, I am going to be stretching. The center is at 1, 0. I'm going to be moving 2 in the x and 4 in the y. So the ellipse looks like this. And if I take values, let's say I go with at t equals 0, sine of 0 is 0, that's a 1. Cosine of 0 is 1, that's a 4. 1, 1, 2, 3, 4. Here I am right now. If I move on to t equal pi over 2, I notice sine of pi over 2 is 1, that's a 3, and cosine is 0. 1, 2, 3, 0. So I notice I'm running in this, even though this says 0 to pi, don't mix that up. And that's going to come up in your homework. At t equal pi, the terminal point, sine of pi is 0, that's a 1. Cosine of pi is negative 1, that's a negative 4. Move 1 to the right, 1, 2, 3, 4 down, and guess what? So again, you could erase the other side, you could just cross it out since you'll be writing with a pencil or pen, but that's it, just the right half of that ellipse. I get to this problem, and here things are a bit tricky, just a bit, not a whole bunch. Here, I'm going to make use of the same idea. I'm going to say, you know what, x squared equal cosecant squared of t. Now, I want to show you another way of doing this. I could square both sides, or I could say, you know what, but I know what cosecant squared equal. That is cotangent squared of t plus 1. And isn't my cotangent, so I could use substitution here if I want. Wouldn't that mean x squared equal y squared plus 1? Or x squared minus y squared equal a 1? Isn't that a hyperbola? You move. And since the negatives along the x, the y, this is going to be one of those or one of those. Well, let's see how that works. If I take t to equal, we're looking between pi over 4 and pi over 2. So if I pick pi over 3, actually pi over 4 is allowed. I didn't pay attention to that. I could start with that. If I pick pi over 4, this will be radical 2, and cotangent is a 1. This is 1, 2, radical 2, 1. I'm right there. This is t equal pi over 4. And since they allowed pi over 2, mine as well. This is a 1. And if I put pi over 2n, that would be a 0. So what does that mean? That means I'm going to only trace this much of the graph. That's it. Anything else is not there. So the graph literally looks just like this. And that's it. Now, I give you an equation, you give me a graph. I give you a graph, can you give me an equation? You do that heavily in chapter 16 of the Calculus, our third book right now, third semester. If I say find a parametric equation, something that you really need to play with. If it's a line, it's really simple to do. Find the equation of a line. So basically, this is what I do. I'm thinking I'll find y as a function of x. And all what I'll do, I'll let x equal t and y will equal f of t and everybody's happy. That's kind of me saying, I'm going to create a vector with this. Let this be whatever it wants and y would be that. And that's really the idea. So, an equation of a line, I know that's y equal mx plus b. Well, let's see. I know that b is 1. And what's the slope? I'm going to rise down 1, 2, 3, 4. And I'm going to run 1, 2, 3, negative 4/3 x. Now, there are so many ways you could really express this. However you see it fit. Oh, that's 1 to 3, that's 4. 1, 2, 3, 4. That's 4 over 4, my mistake. That means that's y equal negative x plus 1. So, I should have used there. 4 down and 4 to the right. There. Well, I could make this a parametric equation with ease. I could say let x equal t if you have y as a function of x, and wouldn't y equal negative t plus 1? And t varies, and this is important. Since I'm letting x equal t, then I'm going to trace this line from the x-axis, from x equal negative 1 to x equal 3, and that will work. And of course, nobody's stopping you from saying, you know what, I don't like that. Instead, I'm going to let y equal t. Well, good for you. If you put a t right there for y, what would x equal? Wouldn't that mean x equal 1 minus y? So x will be 1 minus t. And in this case, t will vary since you're letting y equal t. You would say, let's start at 2 and let's terminate at negative 2. In that order, so that the direction is preserved. So either way, this is easier because we're used to y equal a function of x. That will be y's. Here, I already know the drill. I already know how this works. This is going to be really, this is an ellipse. It's going to be x equal, the stretching in the x is 1 unit, right? And the stretching in the y is 1, 2, 3, 4 units. And if I want, I could write this an infinite amount of ways, really. I'm going to go about it the traditional way, cosine of t and sine of t. And my t, since I am choosing that, I'm going to choose it to be from increasing from bottom to top. Well, here, isn't that t equal negative pi over 2? And I'll check. That will be a 0, that will be a negative 4. Very good. Running all the way to pi over 2. And here it's safe to assume this is going to match because you're choosing x to be a cosine and y to be a sine. But sometimes that's not the way it's given to you, so you got to be careful with that. And there's the homework on page 290, number 7 through 29, odd, 35, and 37.